This chapter is as such hard. Chapter is your machine learning and prediction. This is your second chapter, right? There are two chapters in between which I have not uploaded because I thought maybe I should give you time to first understand machine learning, then I'll upload. So tonight I'll upload those two chapters. But what is more important to understand here is that now we are learning the last part of your machine learning, and we are basically talking about the prediction part, right? So that's the whole objective. Now, it's a tough chapter. Overall, we this whole chapter is divided into three parts: module 1, module 2, and module 3, right? So module 1 is all about your categorical variables, right? Categorical variables, regularization, logistic regression. If I put it in a very simple way, right, this is all about handling your special type of variables. When I say special types of variables, means the variables which are different from the numeric variables, right? Objective is to avoid overfitting and using your logistic regressions or for your classification problems, right? We'll understand all this, guys. The all lot of terms will sound very fancy and very new, but don't get confused, right? Then we have module 2. Module 2 is about your decision trees, ensemble learning, k nearest neighbors, knn, and your support vector machines, right? So these are your more advanced algorithms for your prediction and classification. And module 3 is your neural networks and model performance. Here we step into your deep learning and learn how to measure if our model is good or bad, right? So think of it as your this three modules. As you start very simple in the initial part, module 1, you handle your variables, you handle your regression, you handle your logistic regression. I'll teach you what is logistic regression. Then you move to your algorithms. Algorithm is your decision trees, your ensemble, your support vector machines, your k nearest neighbor, svm, and knn. Then you finish with the advanced, which are the neural networks and your performance measurement, right? So that's the whole objective. You start basic, then medium, then advanced level. Okay, so please listen again. Very very advanced topic, guys. You like my suggestion here is go in that much depth which is required here. Don't try to go into too much of depth because these are very advanced level topics, and the objective of FRM is not to test you on advanced level topics. Objective of FRM is that you understand things uh, in a particular way, right? You understand things in a way where people understand, right? So you understand things from the exam perspective rather than going too deep, because in any one class of 2 hours, 3 hours, you cannot learn it at a very advanced level, right? So remember that point. Okay. All right, guys, let's go ahead, right. So if you look or zoom into your module 1, right, module 1 again is further subdivided into your 6 topics. One is your categorical variables, right? Categorical variables, these are like your these variables like your gender is like male and female na. So you're not saying numeric variables. You are saying that okay, one is a male, one is a female. Or let's say for bonds you have your credit ratings: triple A bond, triple B bond, triple C bond, categorical variables. These are not numeric, so uh, we need techniques like your dummy coding to use them in your models, right? Then we have something called regularization. Now, what is regularization? Please understand a very basic word. Regularization is a technique to prevent your overfitting. Okay, and we discussed in the last chapter last week, right? When your model memorizes the training data, right? So it is not learning, it is memorizing, right? So that is overfitting. We don't want overfitting, right? Because overfitting is like memorization. You are scoring very good in your mock exams, right? But in the real world data set, you're not doing good, right? So memorization is not what we want. So regularization is a technique to prevent your overfitting when your model memorizes the training data set instead of learning patterns. So it kind of adds a penalty to large coefficients in regression, right? So that is your regularization. Then you have something called ridge regression, which is also called as your L2 regularization. Now, what is ridge regression? Ridge regression is you, what do you say, shrink your coefficient, but don't force them to zero, right? So uh, you use this technique, ridge regression, when many predictors have your small effects, right? It's not that one predictor has a major effect. There are many predictors and all those have small effects. Then you use your ridge regression, because in ridge regression, L2 regularization, you shrink the coefficient but doesn't force them to zero. Then you have something called lasso. Lasso is what? Lasso is L1 regularization, right? So lasso here you are shrinking some coefficient to exactly zero now. Now, why are you shrinking some coefficient to exactly zero? Because it works like your variable selection. You are keeping only the important predictors. You are saying that okay, there are 10 predictors. Out of them, 7 are not important. Only 3 are more important. I want to keep only 3. So let me make other coefficients zero. So you are shrinking some coefficients to exactly zero, right? That is your lasso, right? L1 regularization. And then you have something called logistic regression. Now, logistic regression is it is used when the outcome is categorical. Outcome is categorical means yes and no, right? True or false, right? So instead of predicting your exact numbers, you are predicting a kind of probabilities, right? So that is your logistic regression. And then you have something called logistic function and thresholding. You have logistic function which maps your prediction between 0 and 1. I told you it measures your probabilities. We can then apply a threshold that okay, if the probability is above, let's say 50%, we'll take it as yes. If probability is below 50%, we take it as no. If yes, it means it will default. Bond will default. If it is no, it means that the bond will not default, right? So module one, if you just understand the whole understanding, right? Module one is basically teaching you how to deal with your categorical inputs. Categorical inputs, I told you very clearly, like is your gender, male, female, triple A, triple B, triple C. Then how to stop models from overfitting. There you have regularization, L2 regularization, which is making some coefficient smaller. Lasso, where making some coefficient zero. Logistic regression, where you are getting into probabilities, and that's how you classify, right? So again, try to have a story kind of understanding that will help you understand, right? Let's go deeper now, guys. Let's try to dig deeper. Okay, very interesting topic, but very theoretical because this is your introduction to the machine learning world. It is not, what you say, a topic where you have to become master, but it's a topic where you have to know a lot of concept in a decent way, not in the depth way, right? So that's the thing. Okay, now we talk about the categorical variables, right? Which was the first part which I explained, right? Categorical variables, when you talk about data transformation in categorical variables. See, machine learning models works with numbers, right? We understand totally. Now, if you have non-numerical data like your gender, male and female, country, right? India, China, right? Your income ranges means below $40,000, above $50,000, above $100,000, right? So you need to map it into numbers before feeding into the model, right? You have to make a correlation between your data and the numbers here, right? So one way it is done is there is something called one hot encoding, right? So one hot encoding is a method for your unordered categories. Okay. See, guys, I didn't, or as such, lot of things written here. So I cannot write. If I write more, it will confuse you more. My duty in this chapter is notes are very good here. My duty is to explain you difficult stuff here, right? So what you do is one hot encoding. When I say one hot encoding, right, this is for your unordered categories. You use this when categories have no natural orders. Now I say no natural orders. Now let's say you have countries like India, China, Pakistan, Saudi Arabia, US, UK, right? So what do you do is you create a kind of dummy variables where you'll say, okay, country one, right, has certain variable, country two has certain variable, right? And if a country three has certain variable. So let's think about your recently H1B visa news is so big, right? So now if somebody has to apply, this one hot encoding on H1B visa application, you will say that okay, applicants from India, let us give a code called something, right? One alpha zero something, right? Then you will say that okay, applicants from Mexico, you give some other coding, right? Applicants from Cameroon, right? You give some other code, right? So what you are doing, you are not using country names. What you are doing is that you are taking the country names, you are, instead of putting country names in the data set, you are giving the country name some code, and then you are putting the data, right? So that's how you're converting into a dummy variable. And each applicant, when let's say, then they say that okay, India, they will give you so much of quota to India. So if applicant gets then that quota, right, so he gets one, and one dummy variable is 1 and 0, right, he will get 1. And if it is not from that country, he will get 0, right? So that is your one hot encoding, right? That's one hot encoding method. Next is your ordinal kind of encoding. When I say ordinal encoding, this is for ordered categories. Now remember O and O. Ordinal for ordered categories. Your one hot encoding is different. It is for unordered, right? What happens in your ordinal encoding? Ordinal encoding. Use this when categories have a natural ranking and order. When I say natural ranking and order, means you have something like you are putting a natural order that okay, like which Trump is trying to do. He's saying now that your income is above certain thing, you will get more preference, right? So you're putting a thing that okay, low income will get lower points, medium income will get higher points than low income, higher income will get more higher point, right? So instead of making three dummy variables, like for low, medium, and high, what you say is that okay, low is 0, medium is 1, high is 2, right? So what happens by doing this 0, 1, and 2? You are not making now more dummy variables. You are kind of preserving the natural order, right? Again, it's a way of data feeding. Ultimately, we are learning about how to feed data in the models, right? One is your data feeding by one hot encoding, another is your ordinal encoding, right? So when you look at your implementation part, again, if your income is less than $50,000, you are for H1B visa, you will be in, let's say, 0 category. Your income is in 50 to $100,000, you, let's say, you are in 1 category. Your income is greater than 100, you are, let's say, in 2 category. And then you can say income above 153, income above $200,000, 4, right? So this way the model knows that 2 means higher than 1, 1 means higher than 0, and you are able to have a natural order which is preserved inside the model, right? So there are two different ways, right? So key takeaways here, uh, when you're reading this chapter, is that you use your one hot encoding if categories are your unordered, right? uh, which can be your name of the country, etc. In case your categories are ordered, which are ordinal coding, right? Like your income levels, your credit rating, etc. Right? Credit ratings are also ordered. Na? AAA is at the top, then AA comes, and then all that comes, right? So then you use your ordinal encoding, right? So these are two different ways by which you categorize the variables that you need to understand. Okay. All right, guys. Let's move to the next slide. Okay, tough chapter, guys. Focus on learning.
I have a question here.
You go on.
I mean, it's interesting that we are converting the variable into ordinal or transforming the variable. Is to
Right.
what's the reason? What's the benefit for against this?
So see, how do you get your this kind of data in the model, right? How will you see? Ultimately, you are why are you doing it, right? Ultimately, you are doing it for prediction. You are figuring out that I need to predict few things. Now, when you are looking at prediction and you are thinking of using your machine learning methods, right? Then the basic point comes is that how do you incorporate your data which is non-numeric, right? Like the orderedness, the different countries, right? How do you incorporate? See, numbers can be incorporated easily, right? Because ultimately, why do we learn maths, right? In FRM, why do you study maths? Or in fact, in finance, why do you study maths? Because when we are trying to build models, machines understand maths as it is, right? Because maths make clear sense, right? But when you are trying to put your data, which is non-mathematical data, right, you are putting, right, then machines don't understand that, right? So you need to figure out a way that machine understand your non-numeric data. And finance has not of non-numeric data, right? You are trying to see some data of different countries, right? That's a non-numeric things. You are trying to compare things between two countries, non-numeric things. You are trying to order your some certain things when you are trying to understand models, right? Trying to understand credit ratings, non-numeric, right? So overall, when you are trying to learn machine learning, when you're trying to learn algorithms, first point which comes here is that okay, fine, I want to learn your algorithms, etc. But do I have the requisite methods to convert my non-numeric data so that it can be inputted, right, in the machine learning model? Do I have that kind of system or not, right? Ultimately, if you think about how the risk management has also evolved, right, in 30, 40 years back when the risk management started, your Basel group started, earlier it was all English, right? Then what happened? Why did we incorporate quantitative methods in FRM part 1, right? We are converting that English into numbers. We are saying that, okay, we understand risk. Can we have that in percentages and probabilities? Yeah, that's why we learned VAR, value at risk, expected shortfall, right? So overall, we are converting everything into numbers, right? But not every data is numeric. Now the problem comes is, okay, fine, we have converted some things into number, which was possible, but can I convert country names into numbers? I can't do it. Can I convert this different ranges into numbers? I cannot do. Can I have the ordered data in the way, right? Can I have this kind of categories inside my model? No. For that input, especially for the algorithms to work, machine learning things to work, we need to learn all this thing, because these will only be put inside your models. Make sense?
Yes, thank you.
No, no worries, no worries. Right. See, next is your practice question. Very simple, guys. Very straightforward, right? A financing company uses your household income, right? Financing company uses your household income, uh, ranges to model loan applications, right? So the ranges are in, see, the range is there. Ranges are in $25,000 increments up to 200,000, means 0 to 25, 25 to 500, 50,000, 50,000 to 75, 75 to 1 lakh, right? 100,000, 100,000 to 125, 125 to 150, 175, right? Then the last range is anything above your 200,000. If a family has a household income of 85,000, the dummy variable most likely sound will be what? Guys, you tell me. 0 to 25 will be 0.
3.
25 to 50 will be 1. 50 to 75 will be 2. 75 to 100 will be 3, right? So it is 3, right? Again, very simple. This question will not come in exam, obviously. 85,000 falls into your 75 to 100. So this bracket corresponds to your dummy variable, which is 3, right? So dummy variable assigned is 3, guys. I think that's the answer. Let's look ahead. Very straightforward, but this question doesn't, such question doesn't come in exam, guys. This is just to make you understand a little bit that the category has a natural order, so the dummy variables will be assigned starting from 0 with each consecutive range. 0 to 25, it is 0, 1 for 25 to 50, 2 for 50 to 75, 3 for 75 to 100. $85,000 in household income falls in the later range, which means the dummy variable will be set to 3. Okay, that's what we do. Okay, next one is regularization, right? Regularization. When I talk about regularization, again, I told you in the initial part when I was giving you a story kind of thing, what we'll be reading this chapter. Please understand regularization. What is the purpose of regularization? Purpose of regularization is to prevent model from becoming too complex, right? We don't want unnecessary complexity. A very complex model, what that will do is will memorize your training data, which we don't want. Last week we studied, we don't want memorization, we want learning, right? Memorization is your overfitting, right? Overfitting means the model works well on your training data but fails on your unseen data, right? So that's the whole point. And then we'll talk about your ridge and lasso, right? When you look at your ridge regression and your lasso, that we need to understand. These are the two most common regularization methods. Both add a penalty term, right, to the loss function. Uh, Loss function is something which we try to minimize, right? We try to minimize. Okay, loss function is the function we try to minimize in regression is called your loss function, right? Okay, so remember that. So why do we add penalty? Because, and both adds penalty, right, in different ways. Why do we add penalty? Because the penalty kind of discourages your coefficient from becoming your too large. Okay. Now, next is your coefficient shrinkage. When I say coefficient shrinkage, what does it mean? See, regularization is adding a penalty term. So regularization shrinks the regression coefficient towards zero, right? Smaller coefficients when you get mean the model is less sensitive to noise, which reduces your variance on your test data, right? And so smaller the coefficient, better it is. Think of it as you're simplifying the model without losing too much of accuracy. And when I talk about elastic net is a hybrid method, right? Hybrid approach, right? A hybrid approach that combines your Ridge and Lasso both. Why do you want a hybrid approach? You want a hybrid approach because Ridge works well when there are many predictors which are very, very small, but and those are useful. Lasso is different. Lasso is good at selecting only the most important one. So please understand the difference. Ridge is something which has lot of variables, and lot of variables have small effect on a particular thing. Lasso, on the other hand, is different. Lasso has few big variables which have the major effect, right? So both have different kind of usage. Depending on what variables you have, you use that. And elastic net gives the best of both worlds. Please understand the key takeaway here uh, for all of you for exam is that ultimately regularization is a method to control your complexity, right? So that is the whole idea, that you want to control the complexity, right? When you use ridge is also called your L2, right? L2 ridge, we'll study it. Ridge is also called your L2, right? L2 regularization. It ridge means you are shrinking coefficient, right? Ridge is shrinking coefficient.
Coefficient mean terms, betas or betas in regression.
Ah, that's right. It's shrinking coefficient, right? But you shrink it, but you keep all. So you shrink it but keeps all. Lasso, which is L1, right? So this is L2. Lasso is considered L1. This is little different, right? This is again shrinking coefficient, but some coefficient. Shrink some coefficient all the way to zero, right? So it is more focused on saying that, okay, I will only take variables which are major predictors. I will not take something which predicts 5% or 7%. I don't care. So one is focusing on many variables, keeps all, right? One is focusing on only keeping the major variables, right? And elastic net is kind of mix of both, right? So understand it. Okay, we'll go deeper here, guys, now. Okay, so ridge regression. Okay, a lot of formulas will not come in exam, guys.
One question, what's the test data mean? Our sample data, right?
Yes. Yes. Okay. So that's the data we'll use, right? Test data is what we are using for conducting our test, right? So that's what we have. See one. Okay. See, one we have training data, one we have test data, right? Training data is on which the model is trained. Test data is where you finally tested whether your uh, model has actually uh, is test data is your raw data, real world data. See, you train your model on a training data. Once you have trained the model on a training data, right, then when you feel that okay, model is working fine, then you go and take your model into a raw, real world data and test your model there and try to see whether your model is predicting this or model is working in the same way as it was working in your model data in your training data or not. So test data is a new real world data which you have not seen earlier, right? And where you tested your data, right? Last, I think you missed out the last class or something, you're not revised. Please go back and see the last class. There was a lot of discussion on your test data, your training data, and it was, in fact, there are two, three examples also. That training data is something where you train the data, right? Which is you use in different way. Test data is your entirely new data which you have not seen any time, right? So that's your test data. Okay. All right. All right, guys. Next is your ridge regression. Now, I think we have discussed a lot. I'll give you in brief. Again, don't worry about this formula, etc. Those are not coming in exams. They are given in the book, but generally don't come. And these are difficult topics, right? These, they're given it for some reason, but they don't come in exam, right? So when you talk about ridge regression, which is your L2 regularization, right? So first we talk about the data set structure, right? When I talk about the data set structure, when I talk about the data set structure, right? Basically, what you need to understand in your data set structure is that we have your, let's say, n is equal to number of observation, m is equal to your number of features, right? And then you have output variable y, right? So for example, you can use a data set structure to predict your loan default using your uh, income, your credit score, the age of the borrower, etc. Then you have something called model components, right? These model components. So ridge is basically your linear regression with an extra penalty terms. I told you penalties in both lasso also. So you have normal linear regression which uses your intercept alpha and your coefficient beta, which you also told right now. Ridge adds a hyperparameter lambda. So Ridge is adding a hyperparameter lambda to control the penalty, right? This is the penalty term, right? What is the role of this hyperparameter, your lambda? So hyperparameter role is that lambda is not part of the model, right? Lambda isn't part of the model, right? Please remember, isn't part of the model itself, right? It is chosen separately. Think of lambda as your, if you think of very simple term, think of lambda as like a valve or a knob that controls how strong the penalty is, right? So if your lambda is equal to 0, then ridge behaves like a normal regression, normal linear regression. If lambda is large, your coefficient shrinks more aggressively, right? And then you have some coefficient estimation. You follow analytical approach that determines alpha and beta value. Instead of just minimizing your error, ridge minimizes what? It minimizes your error terms. Error term is your residual sum of square, RSS, which you studied, and there's a penalty on betas. This make your betas, your slopes smaller, avoiding your overfitting, right? That's what we do. Then you have your ridge objective. When I say ridge objective, it reduces the magnitude of your slope coefficients by shrinking them towards 0, right? When you look at what you say coefficients which get smaller but never exactly become 0, then there is something called your loss function. Loss function is given as RSS plus your lambda summation of your beta square. What is this term, guys? This is your penalty term. This whole thing is your penalty term, right? Again, this is just for explanation. These will not come in exam, guys. Nobody will tell you to calculate all these things, right? We have explained these things because these are given somewhere in your book, but the question here in exam are mostly theoretical, right? Right, keep that in mind. Penalty term, okay? So penalty term that discourages your large coefficient. Overall, any student, right, who needs to understand, right, please figure out the loss function is the regression objective function, which is RSS, and the second component is the shrinkage penalty for large slope coefficient. The key takeaway here is that when you talk about your ridge, right, ridge is all about, if I had to put in a simple word, if somebody asks me what exactly do you do in ridge regression, I'll say that ridge regression is an extension of linear regression. What do you do? We have linear regression, right? Linear regression, we have RSS, right? But we add a penalty term, L2 penalty, right? We add it. That's why if you focus here, linear regression is your RSS, and L2 penalty is your this lambda summation your beta square. Okay, this is L2 penalty. Okay, so that's what we do, right? Very simple. Ultimately, we are shrinking your coefficient, but please understand here we are not doing like lasso. Lasso, we were eliminating a few of the coefficient. Here we are keeping all the coefficient. Your lambda, which is the hyperparameter, controls the strength of your shrinkage. Okay, that's what we do. Okay, so this is done, guys. Again, understand it. I think I have given you enough idea. Next is your lasso. Lasso is your L1 regularization. When I talk about lasso, right? Lasso, the here idea is your penalty difference, right? Ridge uses square of coefficients, right? Lasso uses your absolute value. Again, it's same. RSS plus your penalty term. Here, lasso is not using square, right? It is using your absolute term, absolute value of your coefficient. This small change makes a big difference in the result. Then there is a parameter determination. When I say parameter determination, lasso doesn't have a very neat analytical solution. Instead, what we do is we use the numerical iterative methods to calculate your alpha and beta. There is something called feature selection, which is a big advantage. Lasso has this advantage. Somebody asks you now that, okay, which regularization is a feature selection. So this is in Lasso, right? Lasso can shrink some coefficient exactly to zero. This means that it effectively removes your unimportant variables from the model. So Lasso is doing your regularization also, which is controlling your complexity. Plus, Lasso is also doing your variable selection, which is simplifying your model. Okay, so these are two things which are working together. Your regularization and your variable selection, right? And overall, then we move to your hyperparameter effect, which is your lambda. Lambda controls the penalty strength. Larger lambda, more coefficient go to zero, more features are dropped. So your lambda acts like a filter. The stronger it is, the fewer variables remain. Then we have the loss function, which is given, I told you very clearly. The first part is like linear regression RSS only. Second part is your penalty that pushes your coefficient towards zero. Overall, as a student, please remember that when you look at Ridge, which is the previous one, L2, that is shrinking coefficient but keeping all variable. When you look at Lasso, it is shrinking some coefficient to zero. It's the feature, extra feature of feature selection, effectively doing your variable selection, right? So remember that. Again, you have to remember this theory only, guys. That will come in exam. So you'll see the question. These kind of questions will come in exam. Which of the following statements about shrinkage penalty uh, terms and regularization is most accurate? Let's see all statements, right? First is penalty terms are not applied in model regularization, right? Penalty terms are not applied or applied? Tell me.
Applied.
Applied. Both cases it applied, right? So wrong.
Yes.
The sum of the squares of the slope coefficient is the penalty term for Lasso. Sum of the squares of the slope coefficient, right?
No.
No, the
No.
squares belong to your what? Ridge, na? In Ridge you have squares, right? In Lasso you have absolute value, right? So that doesn't work. Elastic net sums the penalty terms found in both ridge regression and lasso. Yeah, that's true, right? It's a hybrid approach. The sum of the absolute value of the slope coefficient is the penalty term for ridge regression. No, now which regression is the penalty term? Lasso, right? Right? Lasso, it is there, right? So questions will be like this, right? If you understand theory, questions will be easy here, guys. That's a good part of this chapter. That if you understand a little bit of theory, right, this works, right? So this is done. I think easy question, right? So elastic net is just remember it is using a both hybrid kind of approach. Is a regularization technique where the loss function incorporate penalty terms from ridge regression and lasso. The sum of the squares of the coefficient is the penalty term for ridge, while the sum of the absolute values of coefficient is penalty term for lasso, right? So that makes it very, very simple. Okay. Let's move ahead, guys. Next is your logistic regression. Okay. Logistic regression. This is also very interesting, guys. Okay. First of all, let's try to understand the purpose of the logistic regression. When you see the logistic regression, it is used when the dependent variable is binary, right? This is the condition. Binary means uh, there are only two possible outcomes, right? Lone default, yes or no, right? That kind of thing, right? When the dependent variable has binary outcomes, right? There we use your logistic regression. Linear regression you have studied earlier. Multiple regression also you studied. Now this is a different kind of regression. This is a regression which only works in when the output is kind of binary in nature, right? So remember that. Now what is the key concept here? Key concept here is that instead of predicting the actual outcome, which is done in your linear regression, which we studied in the previous chapter, logistic regression predicts the log odds of the outcome. Log odds, right? There is a term called log odds of the outcome. Once you find, that's why this is the function of log odds, right? When you find out the log odd, then it converts those log odds into probabilities between 0 and 1, right? And for that you have your sigmoid logistic function. Again, you don't have to remember that for exam, just have a idea about it. And if you look at the graph, right, which is shown in the below the slide, right, it's a S shaped, which is low for very negative values, high for very positive values, smooth in kind of middle, right? There are probabilities, right? If event happens, probability is given as, that's the formula for probabilities. Event doesn't happen, right? It is 1 minus event happening probability. Then you have model training. Again, I'm telling you guys, questions will not focus on these formulas. That's not the objective of FRM. FRM just want to introduce. They're giving you a formula mostly for understanding, but not asking in exam. What will come in exam, the formula I'll tell you, right? So let's say if a model predicts your, if a model predicts, then there's 80% chance of default, 20% chance of no default. That's the probability associated with 1 and 0. And then we have your model training. When I talk about model training, there are parameters alpha and beta, which are estimated using a method called maximum likelihood estimation. Again, a very complex method, but remember this, which comes in exam. What is the method used for parameter estimation in your logistic regression? Remember the name. Unlike your linear regression, which minimizes your squared errors, right? Because minimum, what was the method in the linear regression? You were focusing on OLS, right? You were focusing, saying that, oh, I want to reduce the squared error, right? OLS. Logistic regression maximizes the likelihood of correctly classifying your outcomes, right? Which is very weird to understand, but I'll write it here, right? This is very very weird, right? Unlike your linear regression, what happened in linear regression? Linear regression, what are we doing, right? Linear regression, our aim was what? If you have studied the chapters earlier properly, your aim was what? That you want to minimize, right? Linear regression aim was to minimize your squared errors, right? This was the aim of linear regression, right? So squared errors, right? That was you are doing, right? Here, right? Logistic regression, right? Logistic regression is very different, right? Remember this, guys. Logistic regression, when I talk about logistic regression, the objective is to maximize. This was minimize, this is maximize. Maximize the likelihood of correctly classifying outcomes, because the function is totally different, right? There you are saying that there's a lot of noise coming when you're doing linear regression. Your aim was to reduce the squared errors. Here, since your output is only binary, yes and no, so errors are not that important. Rather, you are saying that, okay, I want to have a method of correctly classifying your outcome, right? So that's what we do. Again, you don't even need to go into the mathematics part of it, right? The you know the log likelihood function is defined here, but overall, if you need to think in the exam perspective without looking at too much of formula, please understand logistic regression is for your binary outcomes. You use your sigmoid function, right? This is called logistic function or sigmoid function, right, to map your prediction between 0 and 1. And your model training, when you look at your parameter estimated with your MLE, maximum likelihood estimation, to maximize your probability of correct classification, right? So remember that. Again, don't go too much deep. This is introduction only, so remember that.
One question, can you please explain the log odd concept? This one, it models the log odd of the outcome.
Log odds, right? See,
Yeah.
you are log odds means, okay, fine. See, ultimately, what are you doing, right? You are, when you are trying to figure out, right? When you're trying to figure out your logistic regression, can you find out the probabilities directly, right? You cannot, right? You cannot find out the probabilities directly, right? Why you cannot find out the probabilities directly? Because when your event is binary in nature, right? Binary in nature, then your, it's very difficult to come out with exact numbers. And even if you come out with exact numbers, right, let's say 50%, 40%, and all those things, right, it doesn't add much value, because you are getting what? You are getting a discrete outcomes, right? You want to have your continuous kind of outcome, right? You want to have a logistic function, right? Now when we say log odds, right, what exactly do we mean, right? uh, See, you have in your whatever discussion you have done, your in your quants till now, right? You totally understand that logarithmic distribution is used when logarithmic distribution is used in the scenarios, right, where your, either your outcomes are generally what? Generally positive, greater than zero, right? Because you cannot have your negative values in the logarithmic distribution. Now, when you come to logistic regression, right, you again understand in logistic regression, right, since your dependent variable is binary, right, and you don't want to predict your y, right, which by directly, you try to model the log odds of the outcome. Okay, so now the question comes is that what do you mean by log odds, right? Log odds is a method which is used in your logistic function, right, for a very particular reason, right? So when you, okay, let me write down somewhere a little bit, okay, just for your understanding, right? So what are odds? When I say odds, what are odds? Odds is your probability of success. So you are still finding the probability of success and failure, right? Odds are, you use odds word, na, right? What are the odds of India winning against Pakistan tomorrow, right? Right, India has performed good, so India chances of India winning against Pakistan is very high. Now, so odds is probability of success or failure, right? What is log odds? Log odds, right, which is this model. It is natural log of the odd. Okay, natural log of odds. So what you will do here is you will do log of your, let's say, not the long, log of odds, log of your, let's say, probability of p1 minus p, right? So why do you do log? Right now the question comes, why log? See, odds are always positive. Taking the log converts the range from your 0 to infinity to minus infinity to plus infinity, right? Because earlier I told you, like, logarithmic distribution always have positive value 0 to infinity. Now, when you are converting your thing into your log odds, from your odds to log odds, you are moving from your, you know, your odds were the odds value was between 0 to infinity. Your log odds value is from minus infinity to infinity. So what are you doing here is that you are converting uh, your output, your probability, from a logarithmic distribution to your linear kind of function, right? So you are, basically range is being converted from 0 to infinity. You have converted the range into minus infinity to infinity. And once you convert that, this makes it possible to model them as a linear function. So log odds simply means the logarithm of the ratio of the probability of success by your probability of failure. It is used in your logistic regression because it allows you to transform your probabilities. Why do you want to transform your probabilities? Because your probabilities are bound by 0 and 1, right? And you don't want, it is very difficult to model it in between 0 and 1. You want to have a structure, a linear function, right? You want to move away from a bounded scale to unbounded scale, right? One is a bounded scale 0 to 1, log odds is an unbounded scale minus infinity to infinity, right? And when you move from a bounded scale to your unbounded scale, right, you have converted your basically log odds is your linear function. It becomes a linear function, and once you have linear function, right, that can work very well into your linear regression, etc., right? So logistic regression is what? Logistic regression is nothing but a linear regression used on a binary term. So what we are saying is that, okay, can I have some method by which I can convert my this this problem, right, this binary problem, right, the problem I have, can I convert this binary problem, right, can I convert this binary problem, okay, do I have any idea to convert this binary problem into your, you know, linear function? So that's what I'm achieving, right? So that's a way, right? Again, see, these are all very high level mathematical concepts, but I've given you the logic. Objective is to make the data more suitable for your, what you say, regression, right? That's the whole point. Okay, make some sense?
Oh, yes. Thank you so much.
No, no worries, no worries. Right, these are again, very high level concepts. Okay, next is your logistic function and thresholding, right? So again, I'm telling you guys, there are a lot of things given here. You don't need to read everything, but I'm trying to tell you that much is fine. If you remember that will answer all your questions in exam. When you think about your logistic function and thresholding, what is important to understand is that when you think about your model prediction process, which is given here, right? Ultimately you are using the models for prediction, right? Logistic regression gives the probability, right, in a particular way, right? We then compare this probability with the threshold, right? We find the probability, then we compare it with the threshold z, right? And if let's say we are saying something predict event happens, right, there is a default, and if event does not happen, right, that is something else, right? So what we are saying is that whatever we will predict with your logistic regression, then again we have to test it against a threshold to find out whether it is 1 or 0, right, whether it's default or no default. And the question comes now is that, okay, ultimately what you are finding from logistic regression, you are comparing with the threshold. So how do you estimate the threshold, right? What are the ways to estimate the threshold? So standard choice is 0.5, right, which makes life easier. At 50% you keep it, implies cost of being wrong are equal, right? But there are always your false negative, etc. You have seen your false negative in your type 2 errors also, right? So the whole idea is we treat false positive and false negative as equally costly when you take 0.5, but in real application sometimes costs are unequal, right? So let's say in credit risk, missing a defaulter who is uh, false negative is much worse than wrongly predicting a default, right? So what we do is that we don't keep z is equal to 0.5 every time. We adjust the threshold according to whatever requirement we have. We can keep it 0.1 also, right? We don't want to miss out a person who defaults, right? We want to catch more your potential defaulters, right? So that is what is threshold selection criteria. Don't think that it is always 50%. And then we look at the evaluation metrics for your continuous variable like return. Sometimes instead of just classification, we want to measure the forecast errors. Two common types of errors which have been given in your syllabus are MSFE and MAFE. MSFE is mean absolute forecast error, right? Similar, but take your absolute differences, less sensitive to your, MSFE is mean squared forecast error, and then you have MAFE, right, which is similar in nature, right, to MSFE, right? But here we are using a different term. We are using absolute values. Why we are using absolute values? Because when you use absolute values, then it becomes less sensitive to your outliers, right? So overall key takeaway for any student here who is appearing for the exam, please understand that logistic regression produces your probabilities, right? And then you have to compare that probabilities with a threshold, so called your thresholding, and thresholding converts that into your classification, Now, thresholding choice depends on your cost of error. You can put 0.5, but not in every case. Then you have two evaluation metrics for your continuous variables, such as the MSFE and MAFE. MSFE is mean squared forecast error. MAFE is mean absolute forecast error, right? So these are used when you are evaluating your continuous prediction, example your returns, etc., right? For continuous variable you are using it. Okay, so again, remember these small thing, guys. The good part is they haven't gone deeper here. The bad part is actually also they have not gone deeper. So they just introduce these subjects but don't go too much deep, right? Okay, let's do some question, guys. Again, question will be very easy. For a given logistic regression model, default is assigned a value of 1 and no default is assigned a value of 0. So it's a logistic regression. Because the cost of default is very high on loans the bank expects its consumer to pay back. A reasonable threshold level for that would be what, guys? You tell me. Right? Cost is very high. We just discussed. What should we do? Right? What did we discuss? Cost is very high. We should keep it 50% or less. Tell me. The previous slide, what we discussed. When the cost was very high, what should we do? Come on, guys. I just discussed. Cost is very high. What do we do? I told you, na, thresholding we keep 0.5, but when cost is high, a person failing to detect default risk, Z can be. Did you understand this part? Z can be reduced to 0.1. So what I'm saying is that we cannot keep the same 0.5, right? Because here, if a person who gets away from our model can affect our profit and losses, so we want to have a proper thing, right? We want to reduce that thing, right? Simple example I'll give you, right? What has happened recently? Tata Motors. What has happened in Tata Motors? Tata Motors, there was a cyber attack, right? Cyber attack in Tata Motors. Cyber attack in Tata Motors happened. Now that cyber attack has wiped out. Wiped out what? Wiped out entire year profits. Entire year's profit of Tata Motors. It's such a big cyber attack. I don't know how many people know, right? Tata Motors, I can show you. Tata Motors, just Google Tata Motors cyber attack uh, loss, right? If you just Google, right? Okay, 2 billion pound losses, right? JLR, right? So if you go here, I'll show you, right? Just give me a second. If you so what I'm trying to say is that you don't want such kind of thing, right? You are trying to these kind of things, if it happens in your company, right? One simple thing can cause uh, everything bad, right? So you don't want such high error, right? If I stop sharing and share again, I'm just trying to give you an example, right? Why, when you are trying to look for such things, right? When you see that one error which get away from you, right? That can create such a big problem, right? So if you go here and see, JLR cyber attack takes toll on Tata Motors with potential 2 billion pound loss, right? 2 billion pound is like Tata Motors entire profit a year, right? Production has been halted since September 1, right? Salaried employees have been told to stay home, right? Shutdown extended to September 24. Investigator working on the breach, right? All these things, right? Okay, has claimed, right? Okay, so you can imagine, right? So cost of outage, uh, that JLR is losing about 50 million pounds each week. Its UK plant produces 1,000 vehicles, right? UK government is weighing financial support, right? It is strained, right? Such a big thing has happened, right? And Tata Motors stock is crashing, right? Crashing and crashing and crashing, right? So the whole idea here is that when you have such a massive kind of thing, right? When you are when you know that the cost of losing something, right? Cost of not detecting something is so high, right? Your models must have threshold selection, which is very less, 0.1, even 0.01, right? So that is what we are doing now. So if you think that you, let's say you were modeling what cyber attack, yes or no, right? So keep the threshold 0.01, right? Very less, right? So that's the point. That's the whole point here. So keep it like this, right? So you expect consumer a reasonable threshold level when the cost of default is very high, right? So here we are talking about default, but you can talk about your cyber attack also, and etc. So when cost of default is very high, you keep threshold low, right? You cannot keep 0.00 because that doesn't work, right? You have to keep as less as possible, right? So B. All right, makes sense? Yes or no?
Yes.
It makes sense, right? So remember that, right? That's a simple kind. Again, questions will be like this only, right? The Z value should be low, right? Z value should be low to account for the asymmetry in risk associated with the loan that defaults when unexpected versus when loan payments are met. When you know, uh, right, setting a value equal to 0 is unrealistic, and a value which is zero point 0.5 implies risk asymmetry. So Z of so and so is the most appropriate choice in that situation. Okay, that's what we have. Okay. All right. The next part is your module two. Module two is about your decision trees, ensemble learning, k nearest neighbor, and support vector machines. Right. So these are four topics we'll study. Uh, Decision trees, I told you, I think a little bit earlier also. Decision tree, basically you model your decisions as a tree structure. Okay. You split data step by step, like your yes no kind of thing, and it is very easy to interpret, right? But the problem sometimes comes in decision tree is that there can be overfitting if it is too deep, right? So you need to have a thing that okay, I will not go too deep, right? Then next is your ensemble learning. Ensemble learning combines your multiple models. Now you're saying that okay, we have learned multiple models, why can't we combine multiple models to improve the accuracy? Idea is to have a group of your uh, weak models, right? Weak models means your smaller decision trees that can come together, and then you can have a stronger, more accurate model, right? So in that your ensemble learning, you have something called your bagging, your boosting, your random forest, etc. Right? We'll talk about those bagging, boosting, random forest. Then we have something called k nearest neighbor, which is also called KNN. Right? This is a very simple algorithm. Looks at the k close data points to make a prediction. For example, if most of your five nearest neighbors defaulted, you are also likely to default, right? So it is more about how your neighbors are behaving, right? Works well for your pattern recognition, but can be very slow for your large data sets. And then we have your support vector machine. Support vector machine tries to find the best boundary. Now, when I say best boundary, it is working in your hyperplane. You have seen hyperparameter. Here's something called hyperplane between two classes. So it again in your, if you remember your hyperparameter and logistic regression, there also we were focusing on maximizing the estimate. Here also you maximizes the margin distance between categories for clear separation. Very, very useful for your classification, especially when your classes are kind of overlapping. We'll talk about support vector machine ahead also in detail. So overall, please understand decision trees are very simple. They are simple, intuitive, but very, very prone to your overfitting. Ensemble methods combine many models for your higher accuracy. And then we have KNN, which predicts your thing based on your neighbors' outcomes. And SVM, which is support vector machine, finds the optimal separating boundary. Okay, that's what we have. All right. All right, guys. Moving on, right? Again, this is very interesting and very tricky also. Now we are going to decision trees. Okay, please try to understand, keep the focus, right? Decision tree is, first of all, please understand, a supervised learning method, right? When I say supervised learning method, what do I mean? It means that we know the target, we know the output in your training, right? Supervised is we know the target and output. So it is visualized as a tree structure, decision flow step by step based on your input features. How it works is that each node asks a question about the data. Let's say you're talking about the income. So we'll say that is income greater than 50K? Now, if the answer is yes, the thing will move to a different direction. If the answer is no, thing will move to a different direction. So based on the answer yes or no, you follow a particular branch. Eventually, you reach a kind of a leaf node which gives the final classification or prediction. Where do we use such kind of classification? You use such kind of classification to predict your categories, default versus no default. You use it for fraud versus no fraud. You use it in regression also, predict continuous values like your credit scores, your FICO scores, your interest rates, and together they are often called your carts. Carts means your classification and regression trees, right? And if you think about your interpretability, right, of these models, decision trees are very easy to understand. You can see exactly how the model made its decision, because that's why one of the names of decision tree is also your white box model. Whereas something which is very complex is your neural networks, right, which are very harder to interpret. Those are called your black box model. So white box model, black box model. So overall, please understand in this thing that decision trees are like trees, right? You have a structure, you go from one place to, you have a tree, then you have different branches, yes, no, you move to the leaf node. Decision trees set up your questions leading to your predictions, right? Each stage you will have a question. Is it like this? Yes or no? Is it like this? Yes or no? Right? Useful for your classification and regression. That is why it is called CART, right? Classification and regression trees. And advantage is that it's a very, very interpretable kind of thing. That's why it's a white box, right? That's why. And you will see now, you'll yourself realize that decision trees are the easiest of them, right? This is one of the example, right? Decision trees. Now, in this, you can see, right, that there is a root node, the first split in the tree, which is a root node. It is chosen based on the best feature. So best feature can be your borrower credit score, which best feature can be your sales, best feature can be your growth. So here you have borrower credit score, which is greater than your 740, right? Then you have decision nodes, right? Intermediate splits after the root. So each node is asking another question. When I say another question, it is asking you like, is household income greater than your 100,000, right? Again, yes or no. So these splits further refine the prediction. And then you have leaf nodes. Leaf nodes are your terminal nodes where you have the final output of the tree. And that will give you a classification, that will give you a probability, right? So default probability will come out as like 1.5%, 2%, 3%, whatever, right? So let's say if you are looking in this example, right, which is like bank default probability tree. Step one is to check your credit score, which is greater than 740. Step two is yes, right? If it is yes, then you check if income is greater than 100K, right? If no, check if income is greater than your 150K. And then your final leave gives you default probability or whatever, 1.5 to 2%, right? This shows how a bank can use your decision trees to estimate your borrower risk. What is more important for exam is, please understand that when we think of your root in decision tree, that is a starting split. Then we think of decision node, that is your further splits. Then think about your leaves, which is a final prediction, class, or probability. Then it is easy to interpret, to right, but you must be careful about tree depth. Too much depth you do, then it is overfitting, right? So that's what you need to have, right? That's what you want to understand. Okay. Moving on. Next one is, again, you are having a detailed discussion about decision tree. So this is a discussion about your decision tree splitting criteria. Okay, how trees decide where to split, guys. This comes in exam, guys. If at all a numerical will come, it will come on your Gini index. This Gini index is actually important for exam, right? I have seen some question on the Gini index. Till now, I have not told you to remember any formula, but I'll tell you to remember these three formulas, right? I'm telling you these are important for exam. Right? Till now, I have not told you any formula to remember for exam, guys. But if at all any numerical comes in exam, right, it will come on this: entropy, Gini index, and your information gain, right? So this is important for exam. Okay, not any other formula. This is important. Okay, so the model ask in this case is, which features should I use to split the data? Now the goal is to create your groups, your nodes that are as pure as possible, mostly ones or mostly zeros. Then when you look at your measure of purity, right, because you want to create groups which are pure, right? So measure of purity, when you talk about, right, there, purity or impurity, there you have something called entropy, right? Entropy is your H is equal to minus your summation of pi into your log to your pi, which is probabilities. It will be given to you, right? If it is given to you, just put the values, do the just multiply and pi into log pi, right? Please understand, when you get low entropy, right, please just keep in mind, low entropy is good. Low entropy is good. If you have studied ever physics in life, in your college or school, you should remember that entropy was your too much of movement, right? So entropy, whenever we used to study physics in our school or colleges, entropy we wanted always lower, right? Entropy is randomness, we don't want that. Then we have something called Gini index. G is 1 minus again summation of your probability square, which is lower Guinea, again is pure node, right? Please remember, lower Guinea, we want lower Guinea, right? Lower Guinea is pure, right? So remember that also. Then we have something called information gain, which is your gain of the parent minus your weighted gain of the children. The higher the IG, better the split. Here, information gain, we want higher IG. Higher the information gain, better the split. Okay, so remember these three things. These three things are important for exam, guys. These three formulas are very important for exam. Okay, so if you look at the example here, right, what we are trying to do is we are trying to predict if a firm meets your whatever interest obligations, etc. You have input features, which are your sales change, your bond rating, you have earnings change, your credit sales, your interest, right? So you have a decision tree split, right? Then we talk about your perfect split goal, right? Perfect split goal means split should make your pure sets, right? So ultimately, perfect split goal is you want a pure set. What is a pure set? Pure set is something where all outcomes are the same, like 100% default. Impure set is where your outputs are kind of mixed, right? And if a split is kind of too impure, it provides little predictive value, right? So you want pure set. Impure set has mixed outcomes. If it is too impure, it doesn't add any value, right? So again, I don't think that they will go such deep things here. But if at all they ask you numerical, it will be entropy, gain index, information gain,
What
right?
is
Go on.
it is in log 2? This is log 2. This is
Yeah. We'll go to that, right? That, I think that's a question ahead. We'll talk about that log 2 here, right? So what exactly? Just give me a minute, right? What exactly? It is 2 to the logarithm, right? See, one is natural log, one is your base to the 2, right? You're getting my point. You uh, okay? One is natural log. Natural log is, what is the base in the natural log? They are different. What do we study? There is log 10 also, right?
yes, log 10 we studied, na?
Log 10. This is log 2, right? We are taking the power to 2. Why we are taking the power to 2? Because we have yes and no, right? We have at every stage we are doing what? We are taking the decision yes and no, yes and no. That's why it is log 2, right? The mathematical reason is that, right? We are not taking natural log. The base of the log here is 2, right? That is what we are having. Okay, so remember that point. Okay, we will see the question ahead, you will get more idea. But log 2 is your mostly you are classifying here that you are taking your log to the base 2, so that you are having both things, right? You're keeping in mind your, what you say, yes and no things, right? All right, so now you will see, you will understand more. So when you see decision trees like this example, see, this is what has been done here. See yourself. Now you see here. So you have a data set where you have 16 firms, right? This is you have to do, guys, right? Six firms did not meet your interest obligation. 10 firms met your interest obligation. Now, if I have to find the Gini coefficient, right? Gini coefficient, if I have to find, and if you go back and see the formula for Gini coefficient, what was it? G1 minus summation of pi square, right? G right? 1 minus summation of pi square, right? G 1 minus summation of pi square, right? So what is happening here, right? Ultimately, database is split into your two groups, right? So database has split into one group is 10, right, which met the financial obligation, interest obligation. One group is 6, which did not meet, right? So to calculate your Gini coefficient, which is the base level, we calculate the Gini coefficient to measure how impure or mixed the data set is. So we will take it that, okay, fine, 1 minus one group we have, right, which is, since summation it is, which is 10 by 16, right, 10 by 16 square, because it's 10 out of 16 probability, right? And then you have 6 out of 16, right? Again, right, 6 out of 16 square, right? So this number, which is 0.46875, this number is our baseline impurity, right? This is your baseline impurity. Okay, then we have the baseline comparison. The Gini, your 0.46875 will act as the base value. Later we will compare it with your split to see if your impurity reduces. The more it reduces, the better split it is, right? Then you have something called your root node selection, right? Root node selection. What happens here is, when you're building the decision trees, we pick up the variable feature that gives the largest drop in your Gini. This is called your information gain. If you think about the calculation of information gain, right, this you understand. I told you information gain is also important. And look at the calculation of the information gain, right? Here again, same thing, right? I'm just trying to put it properly, right? Again, you're looking at the calculation of the information gain, right? What is the example we are using? We are using example of sales change, right? We're testing your one variable, whether firms had sales increase or sales decrease. Uh, your case one has sales increase. 9 firms there are total, right? Out of 9, 5 meet your obligation, right? 4 does not meet your obligation. Then we again calculate Gini coefficient 0.49383, and 7 firms also we do it 0.40816, right? So if we have to look at the information gain ahead, right, the information gain is equal to the base Gini coefficient 0.4687 minus the weighted gain of 0.4565, right? So what we have taken is weighted gain of uh, we combine both groups, right? 49383 and 40816. We take the mean value, right? And then we say this one, then this we see that, okay, this results in an information gain of 0.0124, right? This means that the split which was done using your sales change only reduced the impurity by little bit, because I told you, right, this is your baseline impurity, right? And I told you, right, we want lower Gini coefficient, right? So when we did this sales, we are trying to calculate the information gain from the sales change, right? We saw that, okay, by using the sales change, my Gini coefficient actually decreased a little bit. Earlier, my Gini coefficient by 0.46875. Then my Gini coefficient, when you had your 9 firms, right, it came out 0.49383. When I had 7 firms, it came out 0.40816. When you take the mean value, right, it came out your 0.46875. No, sorry, not 0.46, 0.45635. 0.45, 4565. So 0.45, right, 0.0124, right, 0.0124. Okay. And then you look at for your continuous data, like your percentage of sales on credit, there can be many possible split points. The chosen threshold is the one that gives us the maximum information gain. Overall, what you need to understand is first understand how to do this numerical. We start with base impurity. We try splitting with variables. We calculate new weighted Gini, right? And the variable with the biggest reduction in Gini is chosen as the root node, right? So it is more of a method to choose your root node, right? So remember that also, right? Biggest reduction variable with biggest reduction, right? You did it with sales, then you can do it with credit score also. You can do with your ratings also, right? Variable with biggest reduction is your root node, right? The first starting point, right? uh, and again here it was only a small gain which we did. Okay, so all right, so this exam question I have told you how it will come. Okay, so next one is again we are continuing with the decision trees. Decision trees are prone to your overfitting. I told you very clearly. Uh, when do we consider decision tree complete? Right, a tree is finished when either all feature variables have been used, or we reach a leaf, a node that is pure, contains only a one asset class, like either all firms are defaulting or all firms are paying. Right, so either your all features have been used, or when we leave a leaf which is pure set. Okay, key risk is always overfitting. I told you, right? It's simple thing. See, simple things have risk of overfitting. Overfitting means the tree becomes too complex, capturing your noise instead of your useful patterns. If that happens, the model works well on a training data set, which I told you last class also, but poorly on your new data. To control this, we apply your stopping rules, like your limiting tree depth or the number of branches. There are some overfitting controls we need to understand. Overfitting controls is that there is pre-pruning. When I say pre-pruning, you have your early stopping. You stop the tree from growing too much in the first place, right? Don't allow your splits, right? If a node has fewer than 10 observations, that is one point. And then post pruning also, right? Tree, since we are talking about trees, we are talking about pruning. Post pruning is after a full growth. First, let the tree grow fully. Okay, then cut off the branches that don't add any predictive power, right? So one is pre pruning, one is post pruning. Decision trees can overfit if allowed to grow unchecked. We control it by your pruning. Pre pruning stops early, post pruning trims later. So keep that in mind. Okay, very simple. Okay, okay, let's do the question, right? These are the question which comes in exam, guys. I told you numerical will come now. Base your the Gini coefficient for a model is 0.375. This is the base Gini coefficient. The weighted Gini after split is 0.329. Find the information gain, right, of the thing, right? So how do you go the information gain, guys? Like if you go back to your formula, right, what happens in the information gain, right? Your information gain I'm talking about, right? Information gain is your Gini of the parent minus weighted Gini of the children, right? Right. So that's what we do now. In this case, what will we do, right? Again, sorry, right? I've shown you, right? 0.375 minus 0.329, right? Base of the parent was 0.375. Base of the children was 0.329. Very straightforward. Just subtract it. 0.046. 46 plus 29, right? 75. Right. Okay, very simple, guys, very simple, right? Information gain is the difference between a base Gini coefficient and the weighted Gini, right? For this model, the base Gini is 0.375, weighted Gini is 0.329. Subtract it, that's what we get, right? Okay, so keep that in mind. Very simple, very straightforward. Okay, so always subtract your weighted Gini from the base Gini. A higher information gain means a better split, right? So also remember that. Maybe it's not given here. I wrote earlier also in one of the slide. I'm writing again. Higher information gains means better split. Okay. Here the split improves Purity only a little. 2.046. Okay. All right. Next, move to the next one, guys. Ensemble learning, right? When you talk about your ensemble learning, right? I told you ensemble learning was what? You're combining different things together, right? What is informal learning? It means you are combining the output of multiple models, often your decision trees. The idea here is your wisdom of crowds. Wisdom of crowd means you're averaging across model usually gives you better predictions. Also helps you to reduce your overfitting since errors of one model can be balanced by another. The main techniques which are given here is your bootstrap, your aggregation, which is called bagging, your random forest, right? And there is something called boosting also, right? There are three techniques you have to understand. Bootstrap aggregation, which is bagging, we create many decision trees using your different samples of the data. Then we average their predictions. Key point here is that averaging reduces your variance. You get more stable than your one single tree. In sampling, some observations may appear multiple times, other may be kind of left out. The ones which are left out are called out of bag samples used to test and validate the model. When you look at your comparison point, right? Pasting versus bagging, right? Pasting versus bagging. Please remember that bagging is you are sampling with displacement. Pasting is sampling without replacement, right? So remember these small terms, guys, right? You know, random forest. You must have heard random forest a lot of time when you learned about machine learning. Random forest is a special type of your bagging, right? The other one, bootstrap aggregation bagging is a special type of your bagging with many decision trees. Many decision trees makes a forest. It improves your bagging by reducing your correlation between the trees. How do you reduce the correlation? At each split, the model only consider random subset of feature instead of all features. Typically, number of features chosen is equal to square root of the total features. And when you do that, square root, etc., this makes each tree slightly different. Your lower correlation improves your performance, and lower correlation across trees, and you have stronger ensemble performance, right? So in this slide, we're talking about your bagging, your random forest. Bagging is your many trees on different sample, and you are having average prediction. Then there's an improvement, right? There is a next level improvement which is coming on the bagging, which is bagging plus your random feature selection, right? It's similar to what we studied earlier also, right? There was a feature selection, right? Where did we see feature selection? Right, earlier we saw feature selection somewhere, right? Where did we see feature selection? In the first part. Where did we see feature selection earlier, guys? We saw a feature selection in your lasso, right? Lasso was doing feature selection. Here, feature selection is happening in your random forest, right? So random forest is a feature selection, right? Number of feature selection, right? So remember these things, guys. I know these terms are very new to you, but try to remember. The notes here are quite good, right? I'm trying to explain it as in simple words as possible, right? Key benefit of your random forest is you're getting more accuracy, less overfitting compared to your single tree, and both in bagging and random forest. Random forest is much more improvement because correlations are getting decreased, right? Okay, next one is boosting, guys. Boosting is the third method which we had. When we talk about boosting is another ensemble method. Instead of building many trees independently like your bagging, boosting kind of builds them sequentially, right? So each new tree tries to fix the mistake made by the previous one. So there are some types of trees. One is your adaptive boosting, ADA boost. One is your gradient boosting. One is, these are very common, which are given. Adaptive boosting, you kind of start with your small observation, or you start with actually the all observation, not small observation. You start with all observations having equal weights. After each round, you increase the weights of your misclassified observation. This forces the next model to pay more attention to the difficult cases, right? So that's what you do. So you keep adapting the weights, right? Uh, Gradient boosting is different. Instead of weights, it fits the next model to the residual errors. It fits next model to the residual of the previous model, right? The difference between predicted and actual value. This step-by-step correction reduces your errors gradually. Overall, the point here is that boosting is equal to your gradient boosting plus your adaptive boosting. The goal is to improve your accuracy by learning from your past mistake. Each tree is smarter than the last one because it focuses on what went wrong earlier. And then you look at all those things, right? Bagging is more about parallel trees and average results. Boosting is about your sequential trees, each fixes the previous mistake. Then you have adaptive boosting, which weights are misclassified. The weights misclassified cases higher, and gradient boosters focus on residual error, right? So remember that. Again, theory will come in exam, guys. Please remember that. Okay, very difficult things if you go in detail.
Like actually explanatory power of the variables.
Which one?
This is just we study this ADA boosting and gradient boosting.
Okay, what is your question?
Mean, are you talking about the explanatory power? For example, we are going to predict some variable,
Yeah.
let's say probability of default.
So
So, what is the variable element?
these will improve on that, right? So if you think, if you compare with boosting and your random forest, right? These are improving, right? If you compare all these methods, see, decision trees was had a problem overfitting. Then came the ensemble learning. Ensemble learning is better than decision trees. In ensemble learning, your bagging is the simplest one. Then you have random forest, and the most advanced version in ensemble learning is boosting. So the predictive power of your adaptive boosting or gradient boosting is much higher than your random forest, bagging, and your decision trees. Got the idea?
Okay, okay, thanks.
Okay, right. No worries, right? So these obviously these things are much better, right, compared to others, right? All right. Then, in relation to ensemble of learners, which of the following statement best describe the wisdom of crowds? Right? Wisdom of crowd. That makes sense. Wisdom of crowds is what? Right? It is you're taking your uh, masses of people are never wrong. Right? No, that's not what is wisdom of crowd. Wisdom of crowd is it offers the benefits of averaging many prediction. Right? This is the line. I don't think this kind of question comes in exam. Right? It is the basically this is the basic principle behind your ensemble learning, right? That you have wisdom of crowd means you are the benefit of averaging many prediction, right? That's why you are earlier you were talking about trees, decision trees. Now you're talking about your what? You're talking about your bagging, right? And then you're moving to random forest, right? You're taking the crowd, right? Random forest you're going. Then you're talking about boosting, right? So it is again, remember this, it offers the benefit of averaging many prediction. That's why you go into forest, right? Forest and many trees, right? That's what we have. Okay, so this is the part, yeah, produce the best estimate, etc., right? So this is the thing. Wisdom of crowd is evident through an ensemble of learners where many different model predictions are made. They can be averaged to drive a best estimate proxy. For individual models on their own are vulnerable to error. Prediction from multiple models can be averaged to produce the best estimate. Okay, so that's what we had, and then you have KNN, right? KNN. When you talk about KNN, basically, please understand KNN is again supervised machine learning models used for classification or prediction. It doesn't actually learn a model in advance. That is why it is called sometimes a lazy learner, right? It is not learning in advance. It just stores the data and waits until a query or the new point comes in, right? So how does the thing work here is how can it work? It chooses a value of k, which is dependent on number of neighbors to consider. Commonly, there is a number of observations. To define a distance metric like your Euclidean distance, etc. For a new point, you find the k nearest neighbor from the training data. Assign the label based on the majority vote of these neighbors, classification or average, regression. And then you look at the characteristics, right? No training model is built, right? That's why it's a simple algorithm, right? Prediction happens at the query time. Query time, you fetch the data of the nearest neighbors. Works best with your smaller and cleaner data sets when you have smaller observations, because messy data can be slow and inaccurate. And then you have bias variance trade-off, that okay, when you have low k, right, low variables, right, it means you have low bias, high variance, right? Means it is very flexible, fits data very closely, so that's why low bias, but too sensitive to noise, that's why high variance. And when you look at the high k means more smoothing, right? High bias, less flexible, but predictions are more stable, low variance, right? Right. So overall, you need to understand that KNN predicts by looking at your nearby neighbors, not by building a formula. you should look at what you say k, right? You look at the choice of k, right? If you have smaller k, right, you are overfitting, right? Please understand, smaller k leads to overfitting. These are problem with overfitting, which studied last week also. A larger k leads to your underfitting, right? High bias, low variance, right? So again, remember this, guys. These are how do you choose your uh, k, right? K is the what you say number of neighbors to consider. K is number of neighbors. K is not an observation, right? K is your k is number of neighbors. N is number of observation. Okay. So remember that point. Moving on. Next is your support vector machine, guys. When you talk about SVM, right? Support vector machines. When you look at the definition part here, SVMs are again for your supervised machine learning models, right? These are especially useful when we have a large number of features. We have many input variables. The key idea here is very tricky, right? Very tricky. The key idea here is the margin. The key idea, let me write it here. Again, these are very difficult concepts to understand. Key idea here is the margin. When I say the margin, right, the idea here is the margin. When I say margin, see, support vector machines try to separate your classes, right? Classes, what do you mean by classes? It means default versus no default, right? And when you're trying to separate your classes, you are using the widest possible margin, right? So you try SVMs, try to separate, very difficult to understand, guys, very difficult. Separate classes, right, using your widest possible margin, widest possible margin, right, widest path. Okay. And imagine two parallel lines around the data, right? See these parallel lines which are built around the data, right? SVM, support vector machines, chooses the line which is the boundary that maximizes the gap, right, margin between your two groups, right? Then there are support vectors. Support vectors are the data points that lie right on the edge of these margins, right? These points that lie right on the edge of these margins. The separating line, which is the middle of the margin, is the decision boundary. Then you look at your features and your hyperplanes. With two features, right, the boundary is just a line. With three features, it becomes a plane, right? So please understand that two feature, there will be it's a line. Three feature, it becomes a plane. In general, the boundary is a hyperplane, uh, that we need to understand, and there's a trade-off which happens between two features. In the real data, there is a perfect separation may not exist, so wider margin reduces your misclassification risk, but sometimes we accept the narrower margin also to classify more point. This is the bias variance trade-off in the support vector machines. And if you look at the example to understand, right, let's say we are considering your credit score versus your income. So suppose we want to predict your loan default, right? You have features, what in loan default you will use features as credit score plus your income, right? Your features will be credit score and income, right? Now what will happen with SVM is SVM will try to draw a boundary line that best separates the two groups. So you will have defaults on one side and no defaults on other side, right? So again, like, these are very tricky things to understand, right? I will not advise you to go deeper, because then you're not learning FRM, you're learning machine learning that way. But for exam perspective, what I'll give you is the SVM is a supervised machine learning model which is used best for your high dimensional data. The goal here is, right, goal, please understand the goal. I'll write down, right? Goal, which I told earlier also, same like your MLE, right? Your logistic regression, where again the objective was to maximize the probability of classification. Here also the goal is maximizing, right? Goal is maximizing. So remember in your logistic regression, it was maximizing the MLE. Here it is maximizing the margin between two classes, right? Remember that goal is to maximize the margin between your two classes. Okay. Support vectors are the critical boundary points. Output is your hyperplane that separate the classes, right? That's what we do. And then you look at the practice question, right? In practice question, we try to understand in a two-feature support vector machine SVM, the separation boundary is best described as what, right? See, separation boundary, see, recall the concept of SVM, right? SVM tries to draw the widest possible path, right? Widest margin between two groups, right? That is one they want to do. So there are two parallel boundaries which we saw in the graph, right? That lines are at the edges of the path. The data point that touches these edges are called support vectors. The decision boundary lies exactly in the center of the path, right? So when you look at the separation boundary is the center of the path, right? So remember that. Okay. Again, very simple. I think if you remember the uh, graphical representation, I think it will make sense. But again, you know, this is the decision point, right? This is the middle line in between, right? Right. This is your actual decision boundary, right? The center of the part is actual decision boundary, right? Your on the edges, the data points are your support vectors. Okay, so that is what you do. Yeah, so this is what we have in two feature support vector machines. The widest path in two feature support vector machine, the widest path using two parallel lines which separate the observation is created. Support vectors are the data points lying on the edge of the path, while the separation boundary represents the center of the path. Okay, so this is what we have, and okay, all right, guys. Okay, now we are moving to the next one, so we'll take half an hour more extra, guys. So just let's wrap it up. Now we are discussing is the module 3 of this topic, right? Which is neural networks and model performance. Short topic, not very long. So we have studied first two modules where we discussed about a lot of things, right? Including your decision tree, bagging, boosting, random forest, your support vector machines, your KNN, right? So we discussed a lot about them, right? Now we are moving to the module 3, which is neural networks and model performance. Okay. When we talk about neural networks and model performance, what is important to understand is that this is further subdivided into your four parts, right? So first is neural networks. So let me give you a brief understanding of neural networks. Neural networks is basically we'll understand here how neural networks are structured. What are neurons? What are layers? What are weights? What are activation functions? How they can model your complex nonlinear relationships. Then we'll talk about the model predictive behavior, which is how we measure how well a model predicts, and metrics like your accuracy, precision, recall, etc. Then we'll talk about your ROC curve, which is a graphical way to evaluate your classification models, and we'll try to show off the trade-off between your true positive rate and your false positive rate. And finally, we'll move to your logistic regression versus neural networks, which is a comparison between a simpler linear model, which is a logistic regression, which you read earlier, and a more complex flexible model, which is your neural networks, right? Logistic regression we studied in module 1, and we'll try to highlight the advantage versus disadvantage, right? So basically this module introduces your neural networks, then moves on to how to measure and compare model performance, focusing on your ROC curves and compare your logistic regression with your neural nets. Okay, so that's the whole objective of this discussion. Okay, so let's dig deeper, guys. Let's take it one step at a time, right? Okay. All right. So here in this part, we'll talk about your neural networks, right? So the concept of neural network is that we have artificial neural networks, which are ANNs. ANNs are inspired by how the human brain works. right? The most common structure is you have a feed forward network with back propagation. Now this word sounds very difficult, right? Feed forward network with back propagation. Feed forward network is still easy to understand. Back propagation is difficult, right? Back propagation means you adjust the weights and biases, right? Repeatedly. You adjust the base, you adjust the weights and biases repeatedly so that the model learns with each iteration. Okay. Uh, the example, the architecture which is given on the bottom, right? You look at that. Suppose we have three inputs, your x1 and x2 and x3, and we have one hidden layer with two nodes, right, and one output y, right? So how it works is that each output is multiplied by a weight w, right? A bias is added, making it easier for a node to fire, and ultimately, we have the formula also in the slide, and this is how it works, right? Then we have something called your activation function, right? When you say activation function, right, what we need to understand here is that you know uh, after you sum up the weights and your biases, right? After you sum up the weights and biases, we pass it through an activation function, right? This is your activation function given here, right? We okay. So after summing up your weights plus bias, we pass it through an activation function. Example, let's say it's a logistic function, right? Why do we do it? The purpose is to decide whether neuron fires and outputs are clear 0 and 1. Without your activation function, all network would just be kind of linear. Okay. When we have the neural networks, training is very important. You look at the training process. In the training process, you use something called gradient descent, right? Gradient descent. Um, Gradient descent is an algorithm that minimizes the loss error uh, step by step. There is a learning rate. It controls how big each step is. If it is too high, it overshoots. Unstable, it is too low. It's very slow learning. And there's always an overfitting risk, right? When I talk about an overfitting, right, more hidden layers plus more nodes is equal to higher chances of overfitting. Uh, it's overfitting means you're memorizing instead of you're generalizing, which we discussed earlier also, right? So, what are solutions to avoid your overfitting risk? Always try to use validation sets. Always try to use your early stopping. Early stopping means you stop your training once performance on validation steps kind of improve. Overall, right? Overall, there are a lot of points here. As a student who is appearing in exam, please understand neural network mimics the brains with your inputs, your hidden layers leads to your outputs. They learn, right? Neural networks learn by adjusting your weights plus bias via your back propagation plus your gradient descent. And there are activation function which make them kind of non-linear, right? So in this, right, risk is of overfitting, right? Controlled by your validation and early stopping. Okay, so that's what we need to do. Okay, so moving ahead, guys. Okay, next is your about your model predictive performance, right? When we talk about your model predictive performance, there is evaluation tool. Evaluation tool means that is confusion metrics we have, right? So we have the confusion metrics, right? There is this confusion matrix. When I talk about confusion matrix, it's used for model with your binary outputs, example, your default versus no default, right? It summarizes classification result into four categories, which are your, you can see the table, which are your true positive, your false negative, your false positive, true negative, right? Depending on what is the value of your actual positive versus your predictive positive, right? So true positive means, just please listen to it very carefully. True positive means model correctly predicts the positive. False positive means model predicts the positive, but it's actually negative. Positive is false. True negative means model actually predicts the negative. False negative is that negative is predicted falsely. Model predicts the negative, but it's actually positive, right? So false positive is your type 1 error. False positive is your type 1 error. And false negative is your type 2 error. Okay, so that's what we have. Now there are some performance metrics also. Okay, there we have your accuracy, your precision, recall, and error rate. Right. When I call your accuracy is your true positive plus true negative divided by everything, true positive, false positive, true negative, false negative. Then precision we only talk about true positive divided by true positive and false positive. Recall is sensitivity where true positive divided by true positive plus your false negative, and error rate is your one accuracy, right? So overall, uh, as a students, please understand we have confusion metric, your four boxes: true positive, false positive, true negative, false negative. Accuracy is all about your overall correctness. We have precision, how reliable the positive prediction are. We have recall, which is sensitivity, where we look at how well the model capture your actual positives, right? So remember that, right? Accuracy is overall correctness. Your precision is how reliable the positive predictions are. Recall sensitivity is how will the model capture your actual positives, right? So small things, guys. Please try to keep that in mind. You will be fine. And error rates are mistakes made, right? So understand what is accuracy, what is precision, what is recall, and what is your error rate, right? Moving on, guys. The next one, the next one is a practice question. So let's do it, right? The practice question asks which of the following statement best describes when to stop the gradient descent algorithm in a neural network model, right? So this we have understood, right? See, recall the concept when which we talked about. Uh, the function of the gradient descent algorithm is it's a error loss function. Gradient descent reduces this loss step by step. Now during training, the training set, right? Training set error always keeps decreasing. But your validation set error starts to decrease, and after a point, it increases again. This means the model is kind of overfitting. So, uh, training set error always keep decreasing, but your validation set error starts to decrease, and after a point, it increases again. So if it happens, your validation set is decreasing and increasing again, it's kind of overfitting, right? That's why we have to use your early stopping. You stop your training when validation set error starts rising, and since right, so this is what we want, right? When the value for the objective function declines for the validation set, even as it improves for the training set, right? So that is what we want, right? Because if both are increasing, that's bad because it's already too late. Model is falling, right? So this is wrong. So the first one is wrong. Second one, both are decreasing. That's a good stage, but it means that we need to keep training, right? We can't stop, right? We are talking. The question is asking about stopping. When training declines and validation improves, that's fine. You continue it, right? That's fine. You continue it. Question is about stopping. Question is about stopping. So this is uh, fine, continue. Fine, continue. This is about your good stage. Keep training, right? This is both increase, which is already too late. Okay. So this is where we have to kind of stop, right? Because this is overfitting. This is your overfitting, right? When we see this, we need to stop. Okay, so understand all these statements, guys. All these statements depict something else, right? Again, I'll repeat. During training, training set error always keep decreasing. Validation set error starts to decrease, and after a point, it increases again. This means the model is kind of overfitting. Okay, so that's what we want. Overall, please remember as a student for the exam, training error always decreases, validation error first decreases, then start increasing. You stop your gradient descent, right? When validation error increases, even though training error improves, right? So training error decreases when and the validation error starts to go up. This prevents your overfitting, right? Okay. Okay. So, and see the when the value for the objective function declines for the validation set, even as it improves for the training set. Okay. That's what it is, right? So read it carefully, guys. Validation set, training set, understand the difference, right? Yeah, so this is what it is given here also. You know, the whole idea is that to prevent your overfitting, performing calculations for the validation and training data sets at the same time can be done. Moving down the valley will improve both data set objective function, but the point to stop the gradient descent algorithm is the point where the objective function value declines over the validation set, even as it continues to improve for the training set, right? Remember this, guys, very important for the exam, right? Moving on, next is ROC curve, right? That we need to understand. See, ROC curve, when we talk about what is the purpose of ROC curve, right? See, ROC curve is to tell you about the trade-off, right? Trade-off between your true positive rate, which we saw earlier in the sensitivity, right, and your false positive rate, which is your one specificity, right? So, what we have realized over time is that your model predictions improve as the area under the ROC curve AUC increases, right? So these are different values we have to remember. AUC is equal to 1. If it is that the case, it's a perfect classifier. If AUC is 0.5, then it means it's a no predictive value random model. And AUC is less than 1.5, that's zero point 0.5, model has negative predictive power. So you have to see, right? So this area under the curve, right, is a good metric to tell you whether your predictions improve as the area increases, right? So we have to see, right, prediction increases or not, right? So keep that in mind very clearly. Okay, all right. They're done, guys. Next is your comparison between logistic regression versus neural networks. Again, since we studied confusion metrics earlier, right, we have seen your accuracy, precision, recall, right? We also saw that model fit is stronger on training data as compared to validation data, so implying that there is slight overfitting, right? That's what we've seen. So if you look at a training set, both model has equal accuracy. Neural networks had better precision, right? Keep this in mind. This comes in exam. Neural networks have better precision. Logistic regression has better recall, right? So if you have forgotten the definitions, you can go back and check the definition of precision and recall again, right? This is what we talked about. Precision is your total true positive divided by true positive plus false positive. Recall is true positive divided by true positive plus false negative, right? So you have to have clarity about your. See, this is the most important part of your neural network. If you understand these things, you will get, you will get whatever question you will get here, you will be able to answer, right? Precision is your, again, I'll repeat here because this is very important. Accuracy is overall correctness. Precision is how reliable the positive predictions are. Recall is how well the model captures your actual positives, right? So remember that. An error rate is about the mistakes made. Okay. So if now you have understood the definition, right, then it makes sense, right? You look at your what do you say, logistic regression, you realize that logistic regression has better recall, right? And neural networks have better precision, right? So if you want preciseness, you choose neural networks. If you want recallness, you choose logistic regression. When you look at, and this is for training set, right? If you look at the validation, logistic regression has higher accuracy and precision. Neural networks had higher recall, right? So validation set is different, your training set is different. These are kind of contradictory results, right? Because in logistic regression, you have better recall in the training set, but in the validation set, it becomes opposite. Neural networks have better higher recall. In neural networks have better precision in your training set, but logistic regression has higher accuracy and precision in your validation set, right? So contradictory result. Use your confusion metrics for better evaluation. That's the whole point. That you have the data, you can see yourself that if you look at, let's say, your recall, right? Recall, in the training you have 0.297 recall, right? But when you go to your neural network, right, neural network 297 also, which is lesser in your training sample for logistic regression, this becomes 0.345, little bit increase. But neural network, which was 0.228, it increases to 0.380. So it was lesser in the training sample, it becomes higher in the validation sample, right? So these are the results, these are the data points we have got, so you have to remember for the exam, right? So this is what we have. Moving on, guys. Next part here, the confusion metrics can be used to assess your raw data and maybe better reflect the divergence. So follow the confusion metrics, which will help you. Uh, what we have realized also is that the, it depends on the model, right? One model may predict more defaults for one sample, while the other model may predict more default for the other sample. So, depending on what model you choose, your results can vary. So, the set with the highest true positive and true negative rates would therefore differ between the models, right? So, keep that in mind. That it also boils down to the type of model you have chosen, right? The set which has the highest true positives, right, and true negative rates, right? So anything which is predicting the higher value would therefore differ between the models, right? So keep that in mind, and that's what has been answer here, right? You look at outcomes. No default is 322 in your training sample. When you look at your logistic regression validation sample, right, the things were different. Similarly, here you have, in neural networks, you have 82, right? And, when you go to validation sample, it is higher, right? So depending on your choice, right, one model may predict defaults for one sample, while the other model may predict more default for the other sample, right? It depends on the choice of model, and a confusion matrix is used to access this raw data and better reflect the divergence. So we are reflecting the divergence, right? These are things which happen, guys. These are the things which you know, right? Which are very clear to us. Okay, please remember that. Okay, let's do this question now. In a confusion matrix established for a logistic regression model, which two performance metrics must sum to 100, right? Now this is very tricky, right? This is very tricky because if you go back to your definitions, right? If you go back to your definition, then you will realize that, okay, I had so many we studied your accuracy, we studied your precision, we studied your recall, right? We studied different things, right? Precision, accuracy, recall, sensitivity, right? We studied all these things, and when we studied all these things, right, we are focused on the definition. Now we didn't focus too much on your what you say, something above 100, right? But here the question is asking you that what exactly sums up to 100, right? This is interesting, right? So please uh, understand that when we sum the accuracy, right, accuracy metrics, which kind of captures your true positives and true negatives, right? So the numerator of the error rate captures your false positive and your false negative. Both metrics have your all four outcomes in denominator, which implies that when the metrics are added, all four outcomes are in both the numerator and denominator, and the sum must therefore be 100%, right? So you go back and see the formula for uh, your what you say, accuracy and error rate, right? If you go back and see the accuracy and error rate formula, right, you will realize that you add both of them, so you can see accuracy and error rate, right? Accuracy is CUC. Accuracy is this TP plus TN, TP plus TN, FP plus FN, right? And error rate, right? Error rate is one accuracy, right? So again, here the same thing happens. What happens here, right? You have FP plus FN divided by your TP plus TN plus FP plus FN, right? So you are having numerator and denominator both same, right? And then it kind of makes 100%, right? Remember this. This is interesting, guys. Sorry, this is interesting, right? Yeah, this is what we have. So answer is C, right? This is again something to remember for exam. Just keep this in mind. All right. So we go here. This is done. Okay, 100%. Moving on. Next one is confusion metrics on a logistic regression model shows 35 true positive, 28 false negative, 12 false positive, 25. The precision rate will follow the percentage output. See, again, if you know the formula, you are fine. Yeah? If you don't know the formula, I think you will struggle, right? You just put the formula right, you will get it, right? So let's see the formula, right? It all boils down to the formula. You put the formula value, you will get it, right? So precision is equal to 35 divided by the sum of your positive and false positive, right? 35 plus 10, 47, which comes out to 74%. These are 100 total outcomes. The error rate is the false outcomes, so 28 plus 12 divided by the total outcomes of 40%. Recall is the true positive, 35 divided by the sum of the true positive and the false negative, which is 56%. Accuracy is the true outcome divided by your total outcome, 60%, right? So remember this, guys. Again, you have to remember the four formulas I told you earlier also. If you remember the four formula, you will totally fine, right? So that was the question here. So answer is D here, because the precision has been asked. So precision is 74%, right? But practice all those, right? All four, right? My suggestion to you guys is practice all four. That only will help you to whatever will be asked in exam. Exam can ask you your precision. Exam can ask you your accuracy. Exam can ask your error rate. Exam can ask you your recall. You should know the formula for all four of them. Okay. So that's that. This is the end of the chapter, guys. Very tough chapter, machine learning. We have gone in a lot of detail. Please understand the formulas. Please be diligent here. If you try to, you know, not learn this formula of accuracy, recall, precision, error rate, these are very important questions. Learn the numbers of your AOC curve, where AOC is equal to 1 means what, AOC is equal to 0.5 means what, AOC less than your AUC, right, area under curve, right, less than zero point 0.5, that means what. So have that understanding. If you and then look at the divergence between your logistic regression and your neural networks also in the training set, in the validation set, right, which predicts better in the what job your logistic regression does good in your training set, what job your neural network does good in the your training set, and then what exactly happens in the validation set, how things in the validation set. Please understand that. Once you have that understanding, I think you'll be totally fine. Okay. So that's it for this thing, guys. This also completes your neural network. Please go back and revise earlier two modules also, and this module definitely, and your chapter for machine learning is complete. Okay. All right, guys. I'll see you in the next chapter. Thank you.